Imagine this. You're aboard the most advanced spaceship humanity has ever built. Its sleek metallic hull hums with energy, the control panels glow with soft neon lights, and a countdown echoes through the chamber. 3, 2, 1. The engines ignite, not with fire but with something far stranger. The fabric of space bends around you, and in an instant, stars stretch into glowing lines. You surge forward, not at the speed of sound, not even at the speed of light, but beyond it. Galaxies blur into spiraling streaks of color, and distances that once seemed infinite now collapse into moments. This isn't science fiction anymore. It's the future we dream of. But is it possible? Could we ever break the ultimate speed limit of the universe? The laws of physics say no. And yet, history has shown us time and again that the impossible is just something we haven't figured out yet. For over a century, scientists have treated the speed of light as an unbreakable wall. It's the fastest thing in the universe. Nothing with mass can reach or exceed it. This is dictated by Einstein's theory of relativity, which states that as an object accelerates, its mass increases. The faster you go, the heavier you become, requiring more and more energy to keep accelerating. At light speed, this equation breaks down. An object's mass becomes infinite, and the energy required to propel it reaches an impossible level. In other words, you'd need an infinite power source just to get there. And going beyond? That's supposed to be outright impossible. But humans don't accept limits so easily. Throughout history, we've shattered barriers that once seemed unbreakable. In the 19th century, many believed human flight was an absurd fantasy. A heavier-than-air machine couldn't possibly stay aloft until the Wright brothers proved them wrong in 1903. Later, scientists claimed no aircraft could ever break the sound barrier, that the forces involved would tear a plane apart. And yet, in 1947, Chuck Yeager did exactly that in the Bell X-1, shattering the invisible wall at 767 miles per hour. We didn't stop there. Today we have hypersonic jets that push the boundaries of Mach 5, rockets that propel humans into orbit at 17,000 miles per hour, and space probes like Voyager 1 traveling at over 38,000 miles per hour, though even that is only a fraction of light speed. So why is light speed such a unique and terrifying boundary? It's not just about speed, it's about the very nature of time and space. Light travels at nearly 670 million miles per hour, fast enough to circle Earth 7 times in a single second. At those speeds, reality itself begins to warp. Time slows down for the traveler compared to those left behind. This isn't science fiction, it's been tested. Atomic clocks on high-speed aircraft run slower than identical clocks on the ground. Astronauts on the International Space Station, moving at 17,000 miles per hour, age just a little bit slower than we do on Earth. It's called time dilation, and the effect grows more extreme the closer you get to light speed. If you somehow reached 99% of light speed, time would slow down so much that a journey taking mere days for you could mean centuries passing for those on Earth. And that's only at near light speed. Theoretically, if you ever broke the light barrier, things would get even stranger. According to relativity, faster-than-light travel could lead to paradoxes, like arriving at a destination before you even left. In other words, if you could go faster than light, you might be able to travel backward in time. But before we get lost in time travel paradoxes, let's focus on the real question. Is there a way to cheat physics? One possible loophole: warping space itself. Instead of moving through space at impossible speeds, what if we could make space move around us? This is the idea behind the Alcubierre drive, a concept proposed by physicist Miguel Alcubierre in 1994. Imagine a spacecraft that doesn't move in the traditional sense, but instead bends the fabric of reality. By compressing space in front of it and expanding space behind it, the ship would ride a wave of warped space-time, allowing it to reach its destination without technically moving faster than light. If space itself is shifting, the ship remains stationary within its local bubble, avoiding all the energy problems that come with relativistic mass increase. But there's a catch, one that sounds almost as fantastical as the drive itself. To create this warp bubble, we would need something called exotic matter, a theoretical form of energy with negative mass. Unlike normal matter, which has positive mass and is attracted to gravity, exotic matter would repel it, potentially allowing space to curve in ways we've never observed before. The problem? No one has ever detected negative mass or proven it exists. The concept remains purely theoretical, and without it, the Alcubierre drive remains nothing more than a mathematical curiosity. But let's not dismiss the idea just yet. After all, history is full of scientific concepts that once seemed impossible, but later turned out to be real. Black holes were once thought to be a bizarre mathematical construct before we confirmed their existence. Quantum entanglement, a phenomenon Einstein himself called spooky action at a distance, was once ridiculed, yet today it's an established part of physics. Just because something hasn't been observed yet doesn't mean it won't be. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. So, what if the key to faster than light? That travel isn't bending space, but slipping through it. Some physicists believe the universe might contain natural shortcuts, wormholes, hypothetical tunnels through space-time that could instantly connect distant points. If they exist, could we one day harness them for travel across the cosmos? Or is there an even stranger way to cheat the speed of light? You're drifting through the vast silence of space, staring out into an ocean of stars. Even with the most powerful engines humanity has ever built, your destination, another star system, remains impossibly distant. At conventional speeds, it would take tens of thousands of years just to reach the nearest one. Even light, the fastest traveler in the universe, takes over 4 years to bridge the gap between Earth and Proxima Centauri. But what if there were a shortcut, a hidden passage through space-time itself, allowing you to cross the void in an instant? This is the idea behind wormholes, theoretical bridges that could connect two distant locations, making interstellar travel possible without ever breaking the speed of light. The concept of wormholes isn't new. In fact, it traces back to Einstein's theory of general relativity. In 1915, Karl Schwarzschild, a German physicist, found a solution to Einstein's equations that described what we now call a black hole. But buried within those equations was something even stranger, a theoretical tunnel, a bridge between two distant points in space-time. Later, in 1935, Einstein himself, along with physicist Nathan Rosen, explored the idea further. They proposed what we now call an Einstein-Rosen bridge, a structure that could, in theory, connect different regions of space or even different universes. If such bridges existed, they would offer an astonishing possibility: stepping into one, and emerging light years away instantaneously. But before we get too excited, let's talk about the reality of wormholes. First, there's the issue of stability. Even if wormholes could naturally form in the universe, they would be incredibly unstable, collapsing almost instantly before anything could pass through. To keep one open, we'd need something to counteract the immense gravitational forces trying to close it. Once again, exotic matter, our mysterious substance with negative mass, appears to be the missing ingredient. Theoretically, if we could surround a wormhole with enough negative energy, we might be able to stabilize it, allowing safe passage from one end to the other. But as with the Alcubierre drive, there's a problem. No one has ever observed exotic matter in nature. Then there's the size issue. If wormholes exist, they might be microscopic, far too small for a spaceship to fit through. However, some theories suggest they could be artificially enlarged. The idea comes from quantum physics, where tiny fluctuations in space-time are constantly occurring at subatomic levels. Some physicists speculate that an advanced civilization, or even humanity in the distant future, might be able to harness these fluctuations, stretching a wormhole to a usable size. But that would require technologies far beyond anything we currently understand. And let's not forget the time travel paradoxes. If a wormhole connects 2 points in space, could it also connect 2 points in time? Some physicists believe that traveling through a wormhole might allow for time travel, an idea that brings its own set of mind-bending complications. If you could use a wormhole to travel into the past, you'd run into paradoxes like the famous grandfather paradox, where changing one event in history could unravel the future. Could this mean the universe has built-in safeguards against such scenarios, or does the very nature of quantum mechanics allow for realities where multiple timelines coexist? But let's take a step back. Maybe wormholes are too speculative. If we can't bend space or jump through hidden tunnels, is there another way to travel faster than light? What if we could use the very fabric of the universe itself as a kind of propulsion system? There's another radical idea on the table. Tachyons. These hypothetical particles, if they exist, would always travel faster than light, never slower. Unlike normal matter, which increases in mass as it speeds up, tachyons would do the opposite. They'd become lighter the faster they move. If tachyons were real, they might hold the key to a whole new way of looking at faster-than-light travel. Could we one day harness them to propel spacecraft beyond the limits of relativity? Or is there an even more profound solution hiding in the fundamental laws of physics? A crackling transmission echoes across the control panel. You check your navigation screen. Something isn't right. Your spaceship is moving faster than light, but not in the way you expected. Space itself is shifting around you, stretching, and contracting like an ocean of unseen waves. You're not just accelerating, you're surfing on the very structure of the cosmos. If the Alcubierre drive and wormholes seem out of reach, could the key to faster-than-light travel lie in manipulating the deepest laws of physics themselves? One of the strangest possibilities comes from a realm where the rules of reality start to blur: quantum mechanics. While Einstein's relativity governs the large-scale universe, quantum physics rules the subatomic world. And here, bizarre things happen. Particles can exist in multiple places at once, seemingly communicate instantly across vast distances, and even tunnel through barriers that should be impossible to cross. Could there be a way to exploit these phenomena for faster-than-light travel? One particularly eerie quantum effect is quantum entanglement. Imagine you have two particles. No matter how far apart they are, if you change the state of one, the other instantly reacts. It's as if information is traveling between them at infinite speed, violating everything we know about relativity. Einstein famously called this spooky action at a distance. But is it really faster-than-light communication? Not quite. While the connection between entangled particles is instant, it can't be used to send messages or transport objects. At least, not with our current understanding. But if we ever crack the secret of how entanglement works, if there's an underlying mechanism that moves information faster than light, we might discover a way to use it for interstellar travel. Then there's quantum teleportation. Scientists have already demonstrated that quantum information can be teleported over long distances, up to hundreds of miles in controlled experiments. While this isn't teleportation in the way science fiction imagines, where entire people or ships vanish and reappear elsewhere, it does suggest that information can be transferred without physically moving through space. Could a future civilization find a way to scale this process up, teleporting entire objects instead of just quantum states? The idea seems impossible now, but then again, so did the idea of manipulating single atoms only a few decades ago. But what if we didn't need to manipulate particles at all? What if we could find a naturally occurring pathway, a hidden structure in the universe that already allows for faster-than-light travel? Some physicists propose that space itself may contain pre-existing shortcuts in the form of cosmic strings or extra dimensions. Cosmic strings are theoretical defects in space-time, thin, one-dimensional objects that may have formed in the early universe. They could be infinitely long with incredible energy densities, warping space around them like massive gravitational highways. If two cosmic strings were to pass close together, they might create a region where space is so distorted that it could, in theory, allow for near-instantaneous travel between 2 points. Essentially, a natural universe-spanning tunnel without the need for wormholes or warp drives. Then, there's the idea of extra dimensions. According to string theory, our universe may not be limited to just 3 spatial dimensions. If additional dimensions exist, curled up at microscopic scales, There might be ways to fold space in ways we can't yet perceive. Some physicists even suggest that gravity itself might be leaking into these hidden dimensions, which could explain why it's so much weaker than the other fundamental forces. If we could access these extra dimensions, they might provide pathways that bypass the limitations of three-dimensional space, offering an entirely new way to think about faster-than-light travel. And then, there's the most extreme idea of all. What if the very laws of physics aren't as fixed as we believe? Some radical theories propose that the speed of light itself may not be a fundamental constant, but something that can change under certain conditions. In some models of the early universe, light may have traveled much faster than it does today. If that's true, could we one day find a way to manipulate these conditions, allowing us to alter the very fabric of space and time? Right now, all of this remains in the realm of theory, but history has shown us that today's impossibilities often become tomorrow's breakthroughs. We once believed heavier-than-air flight was impossible. We thought breaking the sound barrier would destroy an aircraft. We thought nuclear energy was a fantasy. Every time humanity has encountered a seemingly unbreakable limit, we found a way to push past it. So, will faster-than-light travel remain a dream forever, or are we standing on the edge of a revolution in physics? In our final section, we'll explore the ultimate question. If we ever do achieve faster-than-light travel, what would happen next? What are the risks, the paradoxes, and what might a civilization capable of breaking the light barrier actually look like? You activate the ship's faster-than-light system, and suddenly reality distorts. The stars ahead twist into spirals, stretching and warping as space itself bends around you. There's no sensation of movement, no acceleration, no wind, no friction. One moment, you're floating above Earth. The next, you emerge light years away, staring at an alien sun. The impossible has become reality. Faster-than-light travel isn't just a dream anymore, it's the beginning of an entirely new era for humanity. But what happens next? What are the risks, the paradoxes, and what kind of civilization could we become if we truly mastered the ability to outrun light? The first challenge isn't just about the technology, it's about survival. Space isn't empty. It's filled with cosmic radiation, interstellar dust, and high-energy particles moving at near-light speeds. At normal speeds, these things are harmless. But at faster-than-light velocities, even a single grain of dust could hit with the force of a nuclear explosion. Shielding would have to be nearly indestructible, possibly using electromagnetic fields, plasma barriers, or even manipulating space-time itself to deflect debris. And then there's the problem of navigation. How do you avoid obstacles when you're moving faster than your own ability to detect them? Would we need AI to plot our routes? Or would a civilization advanced enough for faster-than-light travel also have developed ways to predict the very fabric of space itself, seeing dangers before they even appear? And then we get to the paradoxes. Faster-than-light travel isn't just a challenge for physics, it's a challenge for logic itself. Imagine you travel to a distant star and back before a signal from Earth could even reach that location. From your perspective, you took a simple round trip. But to someone observing from the outside, you might have arrived before you even left. If faster-than-light travel allows information to travel backward in time, does that mean we could send messages to the past, change history, create paradoxes where events undo themselves? Some theories suggest the universe has built-in safeguards against such things. Maybe time travel is only possible in certain conditions. Or maybe faster-than-light travel itself somehow prevents paradoxes from occurring. But if it doesn't, then we'd be dealing with a reality where cause and effect no longer work the way we expect. And what about the civilizations that might already be out there? If faster-than-light travel is possible, shouldn't we have already encountered extraterrestrial visitors? The Fermi Paradox, the unsettling silence of the universe despite the vast number of planets, might have a new explanation. Maybe advanced civilizations do travel faster than light, but not in ways we can detect. Maybe they exist in hidden dimensions or travel through wormholes that never intersect our part of space. Or maybe there's something we don't know, something that keeps civilizations from reaching this level of advancement, a limit, a great barrier that no species can pass without consequences. But let's imagine for a moment that humanity does break the light barriers and survives. What kind of civilization would we become? If we could cross the galaxy in moments, we wouldn't just be an interstellar species, we'd be something entirely new. Trade, communication, exploration, everything would be transformed. Entire planets could be as connected as cities are today. Wars could be fought in ways we can't even imagine. And what about expansion? If we could spread across the stars, in an instant would we ever stop? Would we become a Kardashev Type 3 civilization, harnessing the energy of entire galaxies? Or would we discover that there are limits, that even with faster-than-light travel, there are places in the universe we can never go? The truth is we don't know. Right now the speed of light is still the ultimate barrier, but history has shown us that barriers are meant to be broken. What seems impossible today may be common knowledge tomorrow, and perhaps somewhere out there another species has already figured it out. Maybe they're watching us right now, waiting to see if we too will take the next step. So, what do you think? Will humanity one day find a way to outrun light? Or is it a dream we'll never achieve? Let's hear your thoughts in the comments. If you enjoyed this journey through the possibilities of faster-than-light travel, make sure to like and share this video. The more we explore these ideas together, the closer we get to turning science fiction into reality. Until next time, keep looking to the stars.